Today's topic is torque and center of mass. Torque is a topic that we see a lot of in structural designs, in that we have to create stability. When we're talking about stability in a structure, we need to talk about the fact that the sum of the forces has to add up to zero, and that the sum of what we're going to refer to as the torques have to add up to zero. This is the foundation of a three-legged chair. If you only have two legs, the chair will fall over, even though the legs may be able to support the person or object sitting on it. When you put the third leg into the design, stability occurs in all three dimensions. And so what we are going to talk about specifically here is torque. Torque is a rotational, can be thought of in some ways as a rotational force. Torque's equation simply is force times the lever arm times the sine of the angle between them. What does that mean? Well, imagine you have a seesaw. If you apply a force to the seesaw on this side, the other side rises up. And so what we find is that a force applied at a distance is going to cause a rotation. Depending on the location of the pivot point in relationship to the what we're going to call the input and the output forces, we have a amplification of the force, and we have a magnification of the torques as well. So in a very simple problem, if I have an input force of, this is a force, an input force of 20 newtons, and this is applied 2 meters to the right of the pivot point, causing moving in a clockwise direction, clockwise, counterclockwise, there would be that force could support a box or some other object sitting on the other side of the fulcrum. So if I have a box that I set 1 meter to the left, that box is pushing down. And so what we would say is that we would want to counter that force. So again, the force would be countered, action reaction, with the input force. And so what we would do here is we'd say that the sum of the torques, if we want to create balance, the sum of the torques have to add up to zero. And that is that the torques clockwise plus the torques counterclockwise have to add up to zero. We have to put signs on the torques. So the general consensus is that clockwise torques are negative and counterclockwise torques are positive. This follows the notation of the polar coordinate system that goes in a counterclockwise direction. But just like a car going down the road, we get to determine what's positive and negative. Like a ball dropping, we get to decide what's positive and negative. But once we figure out a direction, we must stick with it. So in this case, the torques clockwise, the sum of the torques clockwise would be negative. And so when we realize this adds up to zero, we can move the torques to the other side and then say something like the torques counterclockwise have to equal the torques clockwise, i.e. The force times the lever arm of the clockwise have to equal the force times the lever arm of the counterclockwise. The input force is 20 newtons, and that was the clockwise, and it's acting at 2 meters. So we would say 20 times 2. The other side is acting at 1, and so we could raise up a force equal to 40 newtons. So the lever has amplified the force. Now, this can be done not just with a single mass, but with multiple masses. So if I have a lever and there is an input force of 20 newtons acting at 5 meters, and then there is a second force of 10 newtons acting at 2 meters, and then I want to lift up a box on the other side that is 3 meters over, or more importantly, why don't we approach this by saying, we just did one, we gave the distance. Let's say this box over here is 50 newtons. Where would I place that box? What would X be to balance this off? And so when I look at this, I see 1 counterclockwise and 2 clockwise. And so again, the sum of the torques have to add up to 0. So the torques clockwise have to equal the torques counterclockwise. That means that 20 times 5 plus 10 times 5 10 times 5 has to equal 50 times, around a space there, 50 times x. So 100 plus 50, so 100 plus 50 is equal to 50x. 150 is equal to 50x. X equals 3. So you would place it 3 meters to the left, and that would be balanced off. And you would create equilibrium. Now, while this is happening, there is a downward force of the entire system. And so the downward force of the entire system is 20 plus 10 plus 50 or 80 newtons down, and the board or the pivot point need to push with 80 newtons up. And so the sum of the forces have to add up to 0, 80 down, 80 up, and the sum of the torques have to add up to 0, which would be 150 clockwise, 150 counterclockwise. The one piece of this that we have missed was what happens when the pivot point moves around. Every object has what's referred to as a center of mass. The center of mass of an object is based on the mass distribution of that object. So if I have a uniform object with the weight equally distributed, the center of mass of that object is right in the middle. But when the mass distribution is not uniform, so for example, I have a beam and on the end of it there's I have a beam, and on the end of it there's some sort of T-type structure. This is made out of the same material, uniform material. The center of mass is not located right in the center. It's located closer to the T because there's a lot more mass down in this area down here. If I have a board or other material that is not uniform, for example, I have meter sticks that have been bounced off the floor, have been dented, so sometimes their mass distribution is not uniform, it's not equally distributed, then I can find the center of mass by taking small portions of it. So if this segment here has a mass of 10 kilograms and is located a half a meter from the end of the board, and this segment over here has a mass of 5 kilograms and is located 1 meter out, and this has a mass of 5 kilograms and is located 1.2 meters out, and then I have another 10 kilograms and it's located 3 meters out, and then this whole board was 4 meters in length. If it was uniform and all the mass was equally distributed, the center of mass would be right in the center. But to find the center of mass in a problem like this, we use the equation, the location of the center of mass, x center of mass, is equal to the sum of the masses times their position divided by the sum of the masses. So mathematically, that means that I would do 10 times 0.5 plus 5 times 1 plus 5 times 1.2 plus 10 times 3, and I would divide that by 10 plus 5 plus 5 plus 10. And when I do that, I end up with the values of 5 plus 5 plus 6 plus 30, or 46 divided by 10 plus 5 plus 5 plus 10, which is 30. So I get 46 over 30, and 46 divided by 30 gives us the center of mass at 1.53. So in a 4-meter board, the center of mass is located 1.53 meters from one end, and therefore it is located roughly 2.5 meters from the other. And so that creates where the center of mass is. Putting the pivot point under the center of mass, important. The pivot point under the center of mass, if you put that pivot point there, then what would happen is all the mass on the right would torque clockwise, and all the mass on the left would torque counterclockwise, and we would have balance. It would actually cancel out. So if you create support where the center of mass is, you create if you create support where the center of mass is, you create stability. The other part of this is what happens when you have the center of mass. Let's say this is a uniform board, so it's right in the middle. So this is a 2-meter long board, and the center of mass is located right in the middle at the 1-meter mark. Then we put the pivot point at the 0.5-meter mark. What would happen? Well, this would not be stable. If this was a seesaw, the seesaw would be slanted down like this. It would be torquing in a clockwise direction. And this occurs because the center of mass is creating its own torque. So we need to include the weight of the entire board, whatever it happens to be, into our torque equation. So a problem would look something like this. I have a uniform board that is, in this case, 4 meters long. Uniform means that the center of mass is right in the middle, and the board has a weight of 10 newtons. My pivot point is located at the 3-meter mark. Which is a distance of 1 meter from the right side. What force do I need to put on this right side to keep this balanced? Right now, what we see is we would have, if we were to look at this in a real scenario, we would have it tip like this. What force do I need to put out at the end to tip it back to stability? And the answer to that question can be found by just doing a basic torque problem. There is it's a uniform. Remember, this is uniform, so this is at the 2-meter mark. So this would be 1 meter from the pivot point, and this over here is 1 meter from the pivot point. So that means when we think about it, 1 times 10 equals x times 1. This would have to be a 10-meter board, 10-meter block or something out here to create balance. But the takeaway of this is the pivot point not at the center of mass is causing a torque. The other part of this that we take a look at is something like a scaffolding or a bridge. And so there's a lot of application here in structural design. If we are taking a look at this, we have, for example, a bridge, or maybe this is a roof or something that's supported by these 2 beams. and they have to push up. So if the board on top has a weight of 20 newtons, and this is uniform, so this would be 1 meter out to here. This is 1 meter out to here, and then it's a 4 meter board altogether. So this is located at the 2 meter mark. And let's say that we have a person standing at the 1.5 meter mark, 1.5 meters out, and that person has a force of 100 newtons. And let's say that we have a dog or something standing over here, and that dog has a weight of 30 newtons and is a half a meter from this end. How much force do we see in each of these pillars? The force distribution. You see, as this person up here moves around, I don't think I can grab. Yep, as this person up here moves around, they are going to change the mass, the center of mass of the board system, but more importantly, they're going to apply forces on the different beams at different times. So when the person's over here and they're standing on the board, the board is going to be having additional force on pillar 1 than it does on pillar 2. And when the person is over on the other side by the dog, then there is a force of greater force on pillar 2. So where it's located affects the amount of forces on each of the pillars. And so we have to create a problem that solves for the two variables simultaneously. Whenever you have two variables, you need to solve them simultaneously. You need two equations. And those two equations are very, very obvious. There's the sum of the forces and the sum of the torques. And so what we know is that F1 and F2 are pointed upward. And so the forces upward have to equal the forces downward. That is that F1 plus F2 have to equal 100 plus 20 plus 30. Or in other words, F1 plus F2 have to equal 150. If they don't equal 150, then the whole thing falls apart. We also have to create stability. And so the sum of the torques have to add up to 0. So some of the forces had to add up to 0. Some of the torques have to add up to 0. So that means, again, that the torques clockwise have to equal the torques counterclockwise. And so where is the pivot point? The easiest way to solve this when you have two unknowns in a problem like this is to place your pivot point at one of the unknowns. So I'm going to place the pivot point there, but I'm going to have to do some adjustment in my measurement. So from that pivot point, the person is a half a meter out. From my pivot point, the weight of the board is 1 meter out. From my pivot point, the second pillar is 2 meters out. And from my pivot point, the dog is 2.5 meters out. And so there are 3 forces that are working in a clockwise direction, and there's 1 force that's acting in a counterclockwise direction. And so the torques would go something like this. They would be 10 times 0.5 plus 20 times 1 plus 30 times 2.5 equals 2F2. And so now you can work this backwards to solve for F2. So 10 times 0.5 is 10 times 100. I'm sorry, that was 10 times 100 is equal to 50. 20 times 1 is obviously equal to 20. 30 times 2.5 is equal to 75. And that's again equal to 2F2. So 70 plus 75 is 145. 145 is equal to 2F2. F2 is equal to 72.5 newtons. And so in this particular case, which was total randomization, we ended up with F2 equaling 72.5. If F2 equals 72.5 and we plug it into this equation, F1 is equal to 77.5. And so these values are not the same. It makes a little more sense that F1 would be a little greater because you have this 100 Newton force located closer to F1 than it is to F2. And so the mass distribution on F1 becomes even greater. As the person again moves leftward, that force would increase on F1 and decrease on F2 up until the point where if the board is long enough, if the person gets way out here, they actually will need the pillar to not just push up, but to pull down to prevent the whole thing from tipping like a seesaw. One other topic that we need to address with this is the fact that, and I said it in the beginning, that the torque equation is equal to force times distance, which is the lever arm times the sine of theta. And when we're looking at this, you might ask what the whole deal is, the sine of theta. Well, if I have my force and it's acting perpendicular, we do exactly what we've been doing. But if the force is acting at an angle, whatever that angle is, we only care about the component in the direction of motion. And so when we look at how it makes the angle, we have to plug that in. So if I have a force applied at applied here at a 80-degree angle to the board, that's our 80 degrees, and the force was 15 newtons and the distance was 2 meters, then I don't just do 2 times 15, but I do 2 times 15 times the sine of 80, and that'll give me a decimal answer. 2 times 15 is 30. 30 sine 80 is going to be 29.5. So the torque now is only 29.5. Where did the rest of it go? Well, that's actually going into the component that is, in both of these cases, it's pulling rightward, which means it's literally a force that's trying to pull it out the door. In this case here, I guess it's actually pushing leftward. In this case here, it's pulling rightward, and it's trying to either push the board towards the pivot point or pull it away. So this is information about torque. You're going to try some problems, and as always, if you have any questions, please let me know.